Thank you. I want to talk about a representation that we've not yet discovered, but which we know must exist. It's the representation of a scene that survives movements of the head and the eyes, whether that's large-scale navigation or the very smallest saccades. So the next slide shows an example from computer vision demonstrating one solution to the problem. What you see is that as the camera moves around, it pastes 3D information onto a world-based 3D model of the scene. So the camera keeps moving, but the canvas, if you like, the thing that it's pasting that information onto is stable. So what's the biological version of this stable representation that we've just seen for computer vision? This shows somebody painting on a canvas. The canvas stays still and the paintbrush keeps moving. So it seems likely that the cortex is the paintbrush. But what is the canvas? What's the thing that stays constant despite head and eye movements? So there have been various proposals, including one by Neil Burgess's group, which we see here. And there the idea is, as you move your eyes around this face of Spock, it's grid cells that provide the stable canvas, and that you can paste information from the fovea onto this as the eye moves around. I think that the answer from a neural perspective may be a bit simpler than the Burgess proposal, but it might be harder to think about. So what I'm showing here is a set of Voronoi regions or patches dividing up a space. It's supposed to depict a high-dimensional surface showing neural states that the brain passes through as it carries out a set of actions. So the neural state moves from one point on this space to another, and depending on which region it lands up in, it carries out a different action, and that moves it to a new state. So nearby points on this surface can be reached. I'm not going to define the coordinates of this space, but to say that nearby regions can be reached with simple actions. And if you want to get from the current place on that space to something far away, you're going to need quite a lot of actions. In reinforcement learning, this is called a policy. So that's a set of actions are triggered by S, which is the current state. So a set of states all are linked to a particular action. And this is a familiar idea in the literature. It's been used to model how we might navigate using grid cells, for example. And the training algorithm generates a policy, a set of actions contingent on a neural state. And in this case, it's in 512 space. And it's important to note that what's being generated is not a map, and there's no 3D coordinate transformations going on here. The Dolman-Eichenbaum machine is similar in that it's based on a graph, a set of objects or sensory states, which are the nodes joined by edges, which are actions taking you from one sensory state to the next. So here's a preview of my final slide, just so you know where we're heading. These are things we've said already. We navigate across the surface of potential states using a policy and not 3D coordinate frames. And I'm just going to illustrate that with three cases. One is to talk about egocentric representation. How does that relate to this idea that we're talking about? World-based representation, again, how does it relate to a policy? And finally, processing of object flow. Before I go into that, I want to thank the people involved, in case I forget at the end, particularly in relation to the points I'm going to make here: Alex Murray, Miles Hansard, and Andrew Fitzgibbon. So, The first one is a policy for saccades, and that's going to be a version of an egocentric representation. So S, the current state, includes the current image and the desired foveal image. The action is a saccade that will take you from one to the other. So if we think about an eyeball with the fovea at the back and looking at object 1 in one direction, and object 2 is on peripheral retina currently, but we're going to move the eye to look at it. So the current state S is looking at object 1, desire to look at object 2, and the action is a saccade. So simple, part of a policy network. After the saccade, the eye is moved, the fovea is now, you're looking at object 2, the fovea is on object 2, and if you think of those together, you can put them together into a representation of all the objects that you might look at from this location in space. So the representation over many saccades gives you the visual direction of objects and how to get between them. So that's an egocentric, it's a type of egocentric representation of space. But it's also a policy. Here I'm showing what happens when the optic center moves in space, when you move your head, and that obviously changes the egocentric description of visual direction of objects. So that's a good way to think about optic flow, and we'll come back to optic flow in the third example. I just want to say that even for the very smallest eye movements, so these microsaccades, you can hardly see the eye moving here, but the trace shows how it is actually moving. And that means that objects are jittering around on the retina, even though the relationship between them is stable, and that's what you want to record in the representation, the angles, the saccades between objects. So, second example is a world-based representation. We're going to relate that back to the type of egocentric representation that we've just been talking about. I'm going to change from this surface of neural states to a surface of images because it's easier to talk about. But again, nearby points on this surface could be reached by simple actions, and getting to distant points requires many actions. Okay, I want us to think about you're in a scene like we are here with mountains in the distance, a forest in the mid-distance, and then a picnic table close by. And we're going to think about what effect each of those has on how on the egocentric representation that you might record. So starting with the mountains, the point about the mountains is as you move your head around, the angle between any 2 points on those doesn't change. And so if we think about on this surface of images, all the images where the angles between the mountains are the same, there could be many of them because the mountains are very far away and angles between them don't change. That's less true for the forest. So there's a smaller region of images where the angles are essentially, plus or minus some noise, are essentially the same. And by the time you get to the picnic table, there's a very tiny region of images that are similar despite you moving your head. So an egocentric representation from a single location is at one point on this surface of images, and it has a hierarchical address, with the coarsest version of the address being what happens with the mountains, a medium level with the forest, and a very fine level of telling you where you are using the images that include the picnic table. So the representation of distant objects upon which this hierarchical address is founded is independent of observer translation, that's movement of the head as you walk around, and independent of rotation, that's you making eye movements. And in that sense, it's world-based. Of course, it's not a 3D representation, but in the sense that I'm talking about here, it is world-based. It's not affected by movements of the observer. Right. Animal eye movements help the dorsal stream to navigate image space. This is the third and final example, and I'm going to talk about the dorsal stream and briefly the ventral stream. What I want to take here is a little patch of this overall surface and examine it in more detail to show you what's happening with eye movements. And remember that each of these points on this space is representing a whole egocentric representation. Whereas I want to open that out and have individual surfaces for individual fixated objects. So that's this little patch, and these surfaces relate to what happens to the image when the observer looks at different objects. So the top pink one, they're looking at this face from different locations, but always fixating on the same face. So a surface of images, all with the same object on the fovea. The observer is free to move, but the point is that they cannot escape from this surface for a long time, on average about a third of a second. That's because of the way that animals move their eyes. And eventually the observer makes a saccade and so moves to another surface. And then they can look at another object. And just to point out that essentially all animals have this very peculiar and doesn't happen in computer vision, a very peculiar pattern of eye movements. And if your eyes are fixed to the head, then you will make saccades with the head. And if your eyes are fixed to your head and your head is fixed to your body, then you will make saccades and fixation movements with your whole body, as with this fly. So having set up the idea of surface of images all related by fixating on a single object, we can look at what happens in the dorsal stream when somebody moves. So that's what I'm going to show here. The observer moves while fixating on that person. They move around and now they get a different image. But all through, they've been moving on this surface, they've been fixating that person. So neurons in the dorsal stream, for example MSTD, are especially sensitive to the type of image changes that occur while fixating. That's critical. So they're useful for navigating this surface. So this is a nice experiment that shows how when the observer is fixating and the stimulus is distant, then this cell, this neuron, responds best to motion to the right. Whereas when the observer's fixating again in the same place and the stimulus is near to the observer, that same cell prefers motion to the left. So you could see here what that neuron is responsive to. It's responsive to motion on this surface to the right, as the observer moves its head to the right, crucially while fixating. So that combination of motion and disparity, that complicated receptive field, is only useful if the animal fixates as it moves. So we can finally, we can plot ventral stream. This is not to do with navigation, but we can plot ventral stream neurons, receptor fields on this surface. So they can all be mapped out. So for example, a size invariant neuron has a receptive field plotted out like this. A view invariant neuron has a receptive field on this surface like this, and if you believe in them, then a spatial view neuron has a receptive field like this. So here's the summary slide that I showed you before. We navigate across a surface of potential states, achieving our goals. We store a policy, that's a set of context contingent actions, and the brain doesn't represent the world using explicit 3D coordinate frames and hence doesn't need 3D transformations. We've talked about how you could use this framework to give an egocentric representation, how that's closely related to a world-based representation, and how optic flow, dorsal and ventral stream processing relate as well. And the take-home message, all of these are easier if the brain avoids 3D representation. Thank you.